we have to define pressure. Pressure is equal to force divided by the area. It's how concentrated a force is over a certain area. As far as we're concerned, particles that collide with the walls of a container exert a force on it because their momentum is changing. You will know this from topic 2 when we cover it. Now we know that when the particles collide with the wall pushes back on the particles. This is Newton's third law. So when the particles hit the wall, they exert a force on it. When you have many particles colliding with the surface area, this gives a pressure. From a microscopic perspective, the gas pressure depends on how fast the particles are going, the velocity, in other words the momentum, because the rate of change of momentum gives you the force. And secondly, the frequency of collision with the walls. So if the particles are colliding frequently with the walls, that will apply a lot of pressure. Now we need to state the assumptions of the kinetic model of an ideal gas. These assumptions need to be committed to memory. Number 1, a gas consists of a large number of molecules, not a small number, a large number of molecules. The molecules move with a range of speeds, in other words, a range of kinetic energies. The molecules themselves have negligible volume, have zero volume compared to the volume of the gas itself. The collisions of the molecules with each other and with the container walls are elastic, which means that kinetic energy is conserved. There are no intermolecular forces except during the collision. The duration of collisions is very small compared to the time between the collisions. The molecules obey Newton's laws of mechanics. We need to be able to state the following: that the temperature is a measure of the average random kinetic energy of the molecules of an ideal gas. Here we have a graph showing the numbers of molecules travelling at different velocities. Notice that there is a peak value here. This is the most likely speed because it's the modal value. The average value of the speed is slightly higher, but the RMS value, which is basically the root mean square value, which is used to measure the average kinetic energy, is a little bit higher still. So we know that the molecules have a range of kinetic energies. Some have a very high kinetic energy in this part of the graph. Some have a very low kinetic energy in this part of the graph. So there is a spread of different velocities, kinetic energies. The average kinetic energy gives the measure of the temperature. Explain the macroscopic behaviour of ideal gas in terms of the molecular model. So we need to look at macroscopic and microscopic at the same time. So we have to give qualitative explanations, not quantitative. So we just need to describe. Now when we make these descriptions, we need to look at the particles, the molecules, in terms of the forces and the energies and the frequency of collisions with the walls of the container. I mention specifically because it's the walls of the container. When you measure the pressure inside the gas, we're not interested in the frequency of collisions between the molecules. That does not give the pressure. The pressure is measured by the device which is inserted. In other words, the pressure is measured by the device which is attached to the inside of the wall of the container. So, as you know, when the particle collides with the container wall, it pushes against the wall, which means that the wall must push back. And this pushing force over a certain area gives the gas pressure. So what happens if we change the volume? Let's say we have a larger volume. What will happen? Larger volume means a smaller density. which means the particles have more space to move. They collide less frequency because they have more space with each other, and in particular with the walls of the container, and therefore the pressure will be lower. And with a smaller volume, it's the opposite. If the wall is pushed in like a piston to reduce the volume, we have greater density. The particles will have less space to move. They will start to collide more frequently with the walls of the container, which means a higher pressure. By the way, when you do compress a gas, you actually do work against the gas to make it compress. This work done is force times distance, means that this energy, this work that you're doing, will be given to the particles, so the temperature will also go up slightly because you are doing work. What happens when we change the temperature? What happens if the temperature is higher? If we have a higher temperature, the particles have more average kinetic energy. If they have more average kinetic energy, they have more momentum, which means they will exert more force when they collide with the walls of the container. Also, since they are going faster, they will collide with the walls of the container with a higher frequency. Both of these factors will contribute to an increase in pressure.